Electrical CAD Lab EX704 Computer Program for Optimal Design of DC Machine. Electrical CAD Lab EX704 comes under the department lab as a core laboratory course in electrical and electronics engineering. It is prescribed as per the RGPV university syllabus that a student should know about all the programming code related to the optimal design of DC machine, transformer, alternator, induction machine, cage type, and slip ring, both. In optimal design of DC machine, one is required to understand the output equation of DC machine first, which is nothing but a power equation expressed in terms of various design parameters like specific magnetic loading, electric loading, speed, and the main dimensions. Before we come to the output equation of a DC machine, let us know what these magnetic loading term, electric loading, specific magnetic loading, specific electric loading are to be understood. Total magnetic loading in a machine is a product of total number of poles and the flux flowing in the machine. So the product P into phi is called magnetic loading. Similarly, electric loading is the total number of conductors available in the slot of armature multiplied by the current carried by each conductor. Specific magnetic loading and electric loading gives an rough idea about the size and volume of the machine. Therefore, total flux available across the peripheral surface area of the armature is called specific magnetic loading, whereas the electric loading is the ampere conductors available in a peripheral circumference is called specific electric loading. EMF equation of a DC generator can be converted with proper combination of the voltage equation and current. Replacing the P phi and IZ with the specific magnetic and electric loading, the power equation can be converted to total magnetic loading multiplied by total electric loading multiplied by speed in RPS into 10 raised to minus 3 kVA. By substituting the values for B average and AC, we can get a output equation for DC machine. Output equation of a DC machine is a power equation in terms of C naught multiplied by D square L N, where C naught is called the output coefficient of the machine depending on the parameters like specific electric loading, magnetic loading, and a constant pi square. D square L gives a volumetric estimation of the machine multiplied by the speed in RPS. For computer program for optimal design of DC machine, it is required to first of all calculate the diameter of the armature and length of the armature, that is the main dimensions of the DC machine from the given numerical specifications. Here in this problem, it is required to calculate the total length of the armature and the diameter of the bore of the machine for a 7.5 kilowatt 4-pole 1000 rpm 220-volt DC shunt motor. Specific loadings are given like maximum flux density is 0.9, specific electric loading is 30,000 amperes per meter, field form factor and the efficiency along with the a relationship that a maximum efficiency occurs at full load and the field current is 2.5% of the rated current. Such numericals are to be attempted using the output equation by substituting the given quantities. In order to fit them into the output equation, you are required to calculate the input power of the machine from the output power and also the various types of losses so that the armature power developed can be calculated, and this power comes out to be 8042 watts. When substituted in this output equation gives out a diameter and the length of the armature equal to 0.167 meters and length equal to 0.0921 meters. By understanding the process of numerical, how we go about the algorithm of solving the design equations in case of DC machine, these formulations can be put into form of coding like in MATLAB. MATLAB is a software where the coding is as simple as doing numerical on white paper. By assigning different values of given quantities by various variables, we can directly calculate various steps of numerical as simple as using various design formulations. After making such coding, the calculation output can be found like constant losses, motor current at full load, field current, field copper loss, friction and windage loss, power developed by the armature, and finally the armature diameter and stator core length.